Okay, so welcome at today's day four. Oh, day welcome at today's lecture. This is day four. We are. Pavel, I have some read.ai meeting notes uh, requests recording of this meeting. Should I accept or not?
I don't think so. It is no. Please reject it. It is someone's AI bot, and you know,
Okay,
you should reject it.
okay.
Thank you.
Um, okay. So since now, I need to accept people now manually. So since it is a day four, sorry, of our workshop, we have a lot to go through. I do not have any slides for today, so there will be no drawings of my let's say invention of my own invention. There are enough materials to go through in the notebooks for today and tomorrow. But there are a lot of things to mention here because unfortunately I have seen yesterday when I was going through the workshop materials yet again that I made a mistake. The C underscore if instruction is actually in the workshop and it is used here. Um, I think it is used even in this Q52 or Q60 workshop. I need to see it. I need to look at it. Well, it is used somewhere. So we will have to address this problem. For those of you that did not have downloaded the older version of the library, so for example 1.2, 1.11, and so on, because in 2.0 version of the Qiskit library, this instruction is no longer available. However, there is a workaround that you could import and use in terms of your, let's say, I think it is here in either a super dense coding on teleportation. I think it is in teleportation actually. Um, yes, there it is. C underscore F. So that's the required instruction here because yeah, let's not get ahead of ourselves, and let's start with quantum tomography. Quantum tomography was the notebook that I did not finish with at the day three. This is the last notebook of day three, and then we have the Q60, Q64, Q72. Q68, I think, as well. Oh, there is no Q68. Numeration error. Anyway, we start with quantum tomography, which is a finished lecture of uh, the day three, and then we go with 2 qubits, phase kickback, super dense coding, quantum teleportation, and multiple control constructions. So that's the plan for today. Okay, so first of all, I have good news as well in terms of some of the things that I have mentioned in the day three. Uh, I dug out some of my old code, and we could perform something like seed simulator. This is a way that you can guarantee that on my end, when I will do experiments on my notebooks and you will do your experiments on your notebooks, we will have quite the same, let's say, results. This is not something that is mentioned in the actual materials, but it's very nice addition, I think. So the first thing, let's weave the seed simulator setting in the quantum tomography. Our first topic for today, which is like this. I will edit this to 10,000. So you can so we will have a slightly more precision. Well, there is a thing in let me also run my Epic Pen. There is a thing in quantum information processing that you not only have a, let's say, when you are on the unit circle, right? And we have some state. Let's say we start from 0. Oh, this is. Let's start with state. We start from state 0. We could rotate our state by the gate that was mentioned in the last lecture of day 3. We could apply an R5 gate, right? And rotate our state in this direction to change the state. And now it will be somewhere here. It will be, let's say, C, right? State C, depending on the phi that we use. Now, there is this is something that is quite different from the classical computation, because on a classical hardware there is no probability, there is no possibility of our single bit having a value of between 0 and 1. This is strictly a quantum, let's say, advantage that we have, right? That we can do it. However, when we want to recover if we the information about whether we actually applied this rotation by the angle phi or something else, where there isn't any easy method to do this, because it's still, when we perform a measurement, the state collapses into either 0 or 1. So we still get the binary outcome. We have mentioned that we can alleviate this issue by performing multiple experiments, right? So that's nice, because we can get the, let's say, 121 outcomes of 0, right, out of n, and some other x amount out of n of 1, and this will be our and we can get a, for example, this will be 121 out of n. This will be x out of n. And then this directly corresponds to cosine of phi, right? I have mentioned, and in the notebooks you have the same formula. That this corresponds to this angle that we applied, right? So that's nice, but still we have only mentioned an outcome that is pretty much in this quarter, right? This plus x, let's say, and plus, let me use something else. This 0 and 1. We have mentioned only how that we rotate somewhere around here, right? And when we land here, we get some distribution. However, how do we even get some angles that are going outside of this quarter, right? So if we have state, let's say this one now, this would be some psi2, right? If we rotate to more than pi over 2 angle, how do we get this state? Well, we have the one over here, so that's nice. Now we know that this is actually a negative 0 from one of our previous lecture, negative cat 0. And that is also nice. But once we start measuring, we never get a chance of discovering if we actually went over this negative, right? And this is what and this is where quantum tomography comes in, because it allows us the proper technique of preparing experimentations can reveal whether we were, for example, in this quarter or this quarter, right? So we can expand our circle not only to this quarter where there are only positive numbers, right? Plus on, let's say, if our state was alpha and beta, we would only, if we have rotated the state only in this quarter, right? We would only have a positive amplitudes. But what if we wanted to have a negative amplitude? How can we actually get the result or get any idea that our state is on the other half and reflects this another thing, which is, oh, I am actually near -0 instead of just regular +0. So this is where quantum tomography comes in, and it turns out that after our that when we have some amount of time on our machine, on our quantum machine, because this pretty much ties in only to how much time do we have on our quantum machine. So for example, consider this. We have state. Oh, I have absolutely destroyed my unit circle. Let me rebuild it. Okay. So we have one. So we have two states, right? One is right like here, and one is like here. By on our with the view on our eyes, this state represents pretty much the same outcome in terms of what counts from experiments would we get. But it is drastically different in terms of how this state encodes in our state space. So what we could do is, for example, do this. Okay, I will perform out of, let's say, X amount of experiments that I have. Now let me X encode the number of experiments, so the shots, total shots that I can afford to compute on my target hardware. Let's say I have only a grant for 10 minutes, and this translates to 10,000 experiments on my quantum machine. What happens is that, oh, I need to accept. What happens is that I could divide this amount of shots to first make my original experiments, let's say 90% would be my original experiment. And then I can evaluate what, where am I? Where am I on the unit circle? If this is the case that I am right here, like these two red arrows on the unit circle that are drawn, then I could propose another operation with my 10% remaining time that I have been saving up to this point. So 10% is another guess. Another guess, and this guess will help us after we apply certain operation. This guess can help us decide whether we are on this state, which is plus, or this state where it is minus. How do we do that? Well, recall that we could actually rotate these states. For example, at the end of the experiments, I can still append for this remaining amount of experiments, I can still append some other very simple operation like rotation. And then if if after rotation I get something unexpected, then I know that one of the answer doesn't fit. For example, I could state that, okay, I expect that I am on the plus side. So I am choosing this angle. I could compute it. So there is theta proposed, theta 1, right? Theta proposed. And then after I have my theta proposed, I can apply another rotation gate at the end with theta p, where if my assumption is correct, I should land with my original guess on 0. And if it is not the case, if I still get some ambiguity, then I wasn't at this angle phi p. Because when I rotate this angle around by theta p, I will land somewhere here, right? So I will have around 50-50, right? 50% around. So these remaining experiments will lead me to the correct result, and I can guess what we call a global phase. Global phase is this minus that we see here, right? So this is the method that we could use to, let's say, guess where we were in terms of our global phase. And this allows us to expand further, even further, besides our regular amount of, besides our initial distribution of just 0, 1 that we could have gained when we spent all the time. So 100% of our time on the experiments. And this is the way that we could obtain a global phase. So how do we make it? How do we test against it? Oh, there's some more people. I would like to accept them. Okay, so in Q52, we have a class which is called unknown qubit. This class has some slightly unfortunate naming. They are actually clarified that yes, it is about the shots, but they use the formulation of copies of a qubit. This could be slightly misleading, but they actually mean in this notebook the amount of shots. So, and you can verify that this is actually the case where there is a shots equals self-active qubits. So active qubits is the proposed by us number of experiments that we now want to perform. This is how you would need to read this class that they make in this Q52. I have made yet another modification to this class, which is the seed simulator. This is parameter that you do not have, and I just typed in random zeros and ones. As you can see, this is not binary. This is regular decimal, so this is like 10 million or 100 million or something, 100 million. And I could, from math, I'm sorry, from random, I could import seed. This will help us randomize the angle that is picked during the experiment. This is like experiment. This notebook is involves experiment with some random angle that you don't know at the moment. So what is being set? Well, there is rand range parameter, but also you don't also have this parameter. I'm sorry. I said the class parameter, I'm sorry, object parameter, self underscore underscore seed simulator, which is going to be the same number. And then I use it as my seed simulator parameter. So here it is QASM simulator. This is something that usually I think isn't included in version 2.0. This is old nomenclature, so you would most likely set it to just air simulator by now. Yeah, so let me actually so um, oh, there's another person. So we could do this, and now what do we have? Our regular simulator, we've run this. This is a circuit that gets constructed during the experiment. And now we have shots, which are our active qubits. In these terms, we have to make these active qubits, we need to invoke get qubits first, since the get qubits sets amount of experiments that we will prepare. Then after that, I have a seed simulator. This is a parameter that will set in stone the output of the experiment. So I will run this entire cell with Shift Enter. And now we have our experimentation set. I have changed the number of copies to 10,000 to have some more precision. So let me quickly, oh, there it is, 1,000. Okay, oh, there it is. So now once you run this entire method, you don't have this solved in your notebooks, most probably, but I did solve it prior to our lecture. So for example, let me run this experiment. The 10,000 qubits are created. So we can say that this is like having a grant on the IBM backend. And now they are set to some angle. This qubit is set to some angle. And through the experimentation, we get the results. There are counts that are that are 7,800 and 130 respectively, with respect to 0 and 1. We do have uh, oh, okay. So okay, now it is okay. So first of all, we have this. So we have 8,000 qubits. These were our counts. I'm sorry, I did rerun this experiment. And now we have something like this. I have, after I spent 8,000 or my qubits, so I said that 90%, so here I used 80% of my remaining, let's say, remaining time grant on my machine. I used 80% of it. Then I have obtained the results of my experiment. I did make it so that I have said that this is my proposed angle. This is in radians. So I rotate it in reverse order to rotate it onto the zero. And when we say that this is our angle, I proposed it. Then, if I didn't, if I was wrong, this was our situation. Let me better view it on the actual unit circle. So my angle was very narrow. I proposed, since this is the number of counts that is very close, that I suspect that this might be very close to zero. So my state proposed will be like this, very, very close to zero. Or there is another possibility, which is that it is very close to zero, but to negative zero. Now I propose that in the second step, I say like, okay, this will be my proposed angle. I suspect that we are on the plus side. So what do? I apply a rotation that is in reverse, so clockwise. Because notice that when we apply the R5 gate, it is counterclockwise rotation. And I apply clockwise rotation. So I apply in reverse to what the library does. So here, if I have applied this gate with this rotation of negative 0.1 radian, if I was in this state, I would have observed more counts towards the one. Oh, there is a slight. Uh, I had been on this state, but I am pretty much bang on zero, as you can see from the amount of experiments that I have conducted. 2,000 of them, out of 2,000, actually represent 0. So my error from the actual set state in this notebook is pretty much non-existent. It is like what? 4, 4, wow. Okay, 4 times 10 to minus 3 of a degree. Okay, that's ridiculous. So by that, I can expect this angle to match, and I do suspect, and I have a confirmation that I am on a plus side instead of being on a negative side, where I would have been probably at like 7,700 and around, let's say, 300 experiments towards the one, right? Oh, that is very messy writing. But that would be the result. If I were to decrease the angle from that side, I would have get even more counts towards the one, and instead I completely negated these. So that is how the quantum tomography works, and it helps us decide what is the global phase. To recap, we could spend some of our resources onto thinking about where do we actually are in terms of our global phase. Are we there? Are we there? Or are we there? And we leave some of the resources to not guess, but actually to stop guessing in terms of, oh, I wasted all of them, and I don't know where I was. Was I here? Was I here? Was I here? Was I here? I can have some certain method to actually confirm where I was on the global phase. So that's one thing that is very important in terms of experimental results and interpretation of your calculations that you have performed on a quantum machine. It isn't always very nice to do, because recall that there are two special cases. For example, if uh, I have not a very nice angle. Let's say I have straight up 0. Where am I actually? Am I here or am I here? Well, if I rotate by a set angle, let's say by phi, hmm, when I rotate here and I rotate here, guess what? There is -1 as well, and there is +1. So it is very hard to tell where I am, because after measurement, uh, because after measurement, let me, because after measurement, both amplitudes get squared and I get the same distribution in both cases, no matter from where I land. So this, so where you have these perfect situations that they do not have any difference in terms of, they are pretty much a mirror of itself, right? Notice that this is pretty much a situation where it is a mirror of itself, where you have this situation, then the mirror state, when both of them are moved by the set angle, one of them gets closer to 0 and one of them gets farther out of 0, and it is farther in terms of where would I get? Here I would get a 50-50 again, right? Here I would get like 91% of a 0. So there will be a difference. There will be a hint towards where we are. But in the perfect case, where you pretty much land on either a 0 or a -0, there is very little that you can do with this simple method. But in other cases, it is a pretty good method to do. Okay, so that was quantum tomography, and that was the part that ended the day 3. Now let's move to today. So what we have is pretty much a recap of what I did with the respect of classical bits. This is a 2-qubit representation, and how do we interact with most of the operators? So you probably don't have this filled in your notebooks, but here is the gist. When we had a simple classical bit, a classical probabilistic bit, what we did is we represented it as a certain combination of state 1 and state 0. So this was a 0. Say this is a say this is alpha. This is alpha. This is beta, and beta was 1 minus alpha, right? So this was beta 0, 1. And in the same vein, we said that when we have many of these qubits, right? Alpha, beta. We said that this is a linear combination of now state, let's say A, but now we have 4, like here, right? Get 1, 0, 0, 0, and so on and so forth. And we can tensor product our qubits, no matter how many do we have of these bits or qubits, we could pretty much represent them as a tensor product of these different states, right? And the same applies in quantum world. The same logic of creating those state representations. As you can see here, we have absolutely the same. If we want to represent state 0, 0, we do exactly the same as we said in the state 0, 0 in classical. So this would be the tensor product, right? The 0, tensor 0. This would be it, and we have 1, 0, 0, 0 vector, exactly like here. And for all of the other cases, we would have the same thing. And we could go on as much as we like. Now, what are the operators on these qubits? Recall what we had also with classical qubits, right? If we want to represent many operations on the classical bits, we had to apply identity matrix on this classical bit that we want to preserve, and apply some matrix on the bit that we want to actually change. right? So this is the one that we want to change. So we apply a matrix on it. The same idea happens in quantum representations as well. The same representation. In terms of Qiskit, it actually makes it easy for us. Oh, look, there is this notation that I have told you about. This combined H tensor 2. H tensor 2. Recall what that at first day or at second day, I have presented to you an I tensor 4, which was a 256 element matrix. Since this was like a 4 by 4 compound matrix with, there was an I tensor 2, right? There was some partial representations. I have showed you this. Here we use exactly the same notation to shorten our writing, right? Here we have 16 elements. I will make it slightly bigger so that you can see it on the screen. So this is Hadamard, tensor Hadamard, and if we calculate everything, we had we have a matrix that is filled with 1/2 entries and negatives somewhere where it actually matters. It pretty much comes from the tensor product itself. How do we represent it? How do we actually perform this? Well, we could do this in code twofold, in two ways. So I either apply a single operation of H on the target qubit. So for example, here I had, let's say, quantum circuit with 2. This is a short notation. So for example, I could have been, I could have, uh, I could define, let's say, Q register equals quantum register with 2 and pass it directly. Or I could just have a, let's say, register with no name. And I just pass into the quantum circuit a number. And this number will mean that I have 2 qubits. If I have had passed another number, which is 2, for example, this would mean that I have a classical register as well. So if you want to pass just anonymous registers, that, for example, here I could pass the name of Asha qubits, right? To represent some of the future uses, what happens or what doesn't happen. I could pass a name. This is an advantage of the plain open definition. Where I store it in the variable, I could just invoke a quantum register, instantiate it, and pass a name. However, if I do not want it, I can just pass in a simple number like 2. So here, if I have an anonymous register, what I can do is I can just say quantum circuit.h 0 or qc.h1. And this is exactly what you think. So this is an index from this register, this anonymous register. This would be the index. So these two indices will get, as you can see in the picture, this picture is left, was from the previous instance of the program. So now I can say again qc.draw, and then I can say output mpl, which is output matplotlib. And now, as you can see, it now differs because we have a classical register, as I showed you, that we have this first number, which was a 2 bits. Oh, this should be marked with some other color. So this is the first number, and the second number is classical register, which goes into here. So these are the two ways that you can, let's say, define your quantum circuit. If you want to have a very quick calculation, you can just do this and forget about anything else. But if you want to know some of the interactions, maybe it would be helpful to just name these qubits, because later on they will, let's say, display in the drawing window. This might be advantageous later on, but this requires you to define slightly more code. That's up to you what you use. So later on, so as we can see, we apply a Hadamard on both qubits, right? And this is exactly what happens. So this entire system can be now explained by this entire matrix, which is here and contains 16 elements. But in terms of the actual circuit, look how simple it looks, right? This is very simple notation to remember or to reason about. Way more simple than just saying, oh, I need to I need to perform a tensor product of these numbers, and I would like to, for example, invent my own function to do this and to calculate to calculate all of this, and to maybe print to console this entire matrix. It turns out that you don't need to do this. This is enough. Okay, so that's one thing. Another thing is that, well, what about the library? Well, the library actually, um, let's say, prepares this operation for us. So there is another simulator. So we spoke about state vector simulator, which after all operations, we do not append a measure in our circuit. Instead, we run a state vector simulator, and it poses the entire vector of all amplitudes, right? It calculates it for us and presents us in the as a list. So if I wanted to say, for example, if I have a 1 square root of over 2, 1 square root of over 2 state, I could have run a state vector simulator. A state vector simulator. If I wanted to run a job that simulates actual outputs from a quantum computer, I would run R simulator. And now if I want to see what operations did I perform and how do they look in the matrix form, I have a unitary simulator. So unitary simulator gives me output that looks exactly like this matrix, right? So instead of the state, instead of the vector as an output, I get a matrix, right? This is the unitary simulator. Result. Right? This is the unitary simulator result that and sometimes you want to do this because you would like to see all of the calculations that you would make on the actual machine. So this is very important. And here I also, let's say, made my own implementation of how do I print this matrix, because as you can see, I have it very nice and kind of very evenly distributed. So I could give you this code. Later on, you can replace it with what you have um, by default in the project once you download it, because this representation is quite more pleasing to my eyes, let's say. I cannot really describe describe it to you, but this is exactly what I think. This is slightly more sophisticated because it uses the f-string notation from Python, and it uses this for a string formatting, uh, let's say notation that you can paste into your bracket. Once you have a format string, right? Wait, that is not an f, that is something completely else. Once you have an f string, then you can perform a bracket, do some operation, and then make an exclamation mark, uh, pass in a format. So this is a string, and the number of characters that it will, let's say, justify the content towards, right? So it will have an 8 characters and 7 characters as a soft and hard margin. This is something like that. You have to look up the Python standard to actually decode what it means. So there is very short, in short, there is a string format, and after a colon, I leave like soft and hard limit on the number of characters that needs to be rendered. So for example, in this block of text, let's say not this one, but this one, right? And this will be always right justified. There is a setting for it as well, but this is not a Python tutorial, so I will leave it up to you to look it up. So here again, we have a quantum circuit. Now we are applying, this is another task, very simple, yet again, I have solved this. There is very not much problem to it. There is a reverse bits as well, nomenclature. So in terms of reverse bits, you will have some sort of a different ordering. So here, for example, you see the up qubit is Q0, and when I perform a reverse bits, then the up qubit starts from Q1. So this is sometimes nice if you want to, let's say, align your reasoning towards certain notation. For example, most significant bit, least significant bit, and you are, um, let's say, you mistake one for the other. You could fix the drawing like this and kind of reason about it in your own way. This is also a method that you could use. So here the same method. Now we investigate the in both of these tasks that are presented to us in Q60. We either want to display the result of a single uh, H tensor H and H tensor I. So, and what is the implication when we do a unitary simulator? And the implication is very straightforward. So in H tensor H, every single entry is 1 square root of over 2 multiplied by 1 over square root of over 2 is 1/2, right? And there are some entries that are negative based on our tensor product. But here we have something different because we only on diagonal we see that there is an H tensor I, right? Oh, I'm sorry. We see that there is H tensor. No. Yes, actually, yes. So H tensor I, and then we see that we distributed 1 over square root of 2, 1 over square root of 2, and there was multiplied by I. So yeah, so there was a tensor multiplication. So now regular X, I will make it like that. 1 over square root of 2, and then so here is minus, as we can see, multiplied by I, and this was the matrix. So pretty much what we can reason about, it. The unitary simulator is here to help us to reason about the operations that we apply on different qubits and operations. And here we have a regular matrix multiplication of H tensor 2 against some of the states, and we have been presented in this. We are presented in this notebook the different ways that we can reason about the multiplication and the construction of these states. So here, for example, as I have showed you previously, this column vector. Okay, I see the second entry, so I take in the second column, and that's exactly it, right? Or I could say that I just apply Hadamard to each of the qubits because I could just split it in the tensor product and distribute it tensor one tensor, and I could just distribute this like this, right? Because now I have H tensor tensor H tensor. So this is our H tensor 2, right? And I could distribute this somewhat differently. Below and here is the full notation. Here is yet another case. You have you can check it out at your own leisure. And now we have a CNOT. So the CNOT is exactly the same operation as we have done with the classical probability. The CNOT is here, it is denoted as the CX operation. So if we measure it, we also instantiate a quantum circuit with anonymous registers. And for each pair, we can check what are the for each pair of the input. I will also make a barrier right here. So you can see barrier. Barrier, by the way, is actually, let me do this. Okay. So barrier is the, let's say, instruction that in quantum hardware synchronizes all the qubits in time. So for example, the quantum hardware will actually wait until all of the operations are done on the left side and only then start processing the other side. And yet another case of it would be, for example, as soon as possible. This is the type of processing, and this doesn't involve the barrier instruction. This is just whenever the qubit is free, you shoot a laser on it if you have an operation like a single X, right? Because what you could do is, for example, you could have a control operation here, and then you have yet another operation here, and then you could have a barrier, and only after a barrier, this operation, like let's say Hadamard, would be applied on the first qubit, right? So, so this barrier doesn't allow this operation to come into this slot. And if there is no barrier, then this operation, this Hadamard, would happen already at here. So this is the difference between a no barrier and barrier instruction when you make it on the actual hardware. So let's move on with the phase kickback. This is pretty interesting phenomenon during the operating on a on quantum resources. And it works like this. In certain cases, when you entangle the qubits, and we have uh, four different distinct entangled states, right? I didn't mention them, but there are four different ones. And these are called Bell states, right? Bell states. And these are entangled states. You can look up the names actually in the internet, but for short, you have a capital Phi states and you have capital Xi states. And what they mean is that there are four of them, four unique combinations. So what I can have is that both qubits are the same, plus yy over 1 over square root of 2. We are these Bell states actually encode a quantum entangled states of 2 qubits. So we are not talking about like multiple qubits, like 7, 19, nothing like that. The Bell states only describe 2 qubits that are entangled always. So we have a set of states that both of the qubits that are the same. So for example, here are 0, 0, 0, 0, and 1, 1, right? So if you know the value of one qubit, let's say Q0, I will have from measurement, after measurement, I know that this is 1. Then I already know that Q1 is actually the same, the exact same, right? And this is one type of the states, of the Bell states. Yet another type of the Bell states is when we know that it is actually let's say, anti-complement, right? Because there is 0, 1 and 0 and a 1, 0. So if I know that Q0, let's say, is a 1, then there is no other possible outcome than Q1 being 0, right? So it is like anti-complement. I call it myself. This is not something that you will see in any paper. This is something that I use for myself to easier memorize. So these are complement because every single, I'm sorry, not every single. When you measure one, you know the other, and the other is always the same. And in this case, the other is its own, like, let's say, the other option. When you have one option on the one qubit, it's the other option that you see on the other qubit. There is a version to it. There are versions to it, to them. That's why there are 4 of them. So as you probably can guess, there is a plus and a minus. Why is that if it is not the case that you know? Well, there can be a negative and positive phase in them. So I mean the vector components that encode these states can be positive or negative, right? So I could have, let's say, 1 over square root of 2, 1 over square root of 2, and then 0, 0. But I can have a plus and minus here, or minus and minus. So there is different possibilities to this, right? And not always uh, you get the same result every single time, even though you get the same amount of outcomes, right? You have 2 outcomes of 0, 1 and 1, 0. The phase could be different between each other, and you won't see it with counts. So these are the Bell states. I forgot to actually mention them in the previous lecture, but this will come into play today and with this thing. So, so what is the phase kickback? Sometimes after applying a certain operation, what we get is not exactly what we would expect. And this is exactly one of these situations that only happens in the quantum environment. So let me print this circuit. What do I do here? Circuit dot draw output MPL. Seed simulator, I do it here even, but let me print the circuit. So what I do here is I set my register for this exact, uh, let's say, for this exact, with this exact recipe. So we start, let's first set these states. We start in a quantum state 0, 1. Well, we always start at 0, 0. So we need to prepare this one, right, at first. So that is why we have to apply our X gate to our qubit 0. So notice that there is a certain notation to it. So this is least significant bit. This is most significant bit. So the least significant bit starts from the far right. And then what do we do? Apply Hadamard to both qubits, apply CNOT operator, where the controller qubit is Q1 and the target qubit is Q0. And then, yet again, we apply Hadamard to both qubits. So this is our circuit. And what do we even achieve here? Oh, I do not have a... Okay, so P here equals, I will import from lib import pyplot as PLT, and I will also do plt.show. I think this should be okay. No, it isn't okay. Okay, that's fine. Maybe I move this at the end. This will take, yes. Okay, we managed to. So one thing to come back to. We start in state 0, 1. I'm sorry for the slight technical problems. We start with state 0, 1, right? Then we apply this strange mix of gates. At least for me, this was very strange when I started out. Why do we need to apply Hadamard and then some CNOT and then some other Hadamards yet again? What does it even mean? What does it do? Well, it turns out that it does something magical. And this is like, we don't expect it at first, right? Because we do apply some Hadamard, right? So, okay, we do this quantum flipping, quantum coin flipping. Then we apply a CNOT. So, okay, that's like something we also know, right? So if the first qubit is 1, we flip the Q0, and we apply then Hadamard again, right? So we do this. So we yet again, like, coming back uh, from this state of plus, it turned out to be, maybe it doesn't. It did feel to me like this. That is why it wasn't so, let's say, intuitive at first. Because we do something like this, like Hadamard, then we do a CNOT, right? So we do conditional X, then we yet again go back to 0. What is happening here? It turns out it does have a pretty significant implication, and it is playing with our result, because we get 1, 1 when we measure both of these qubits, and we get it always. No matter how many experiments do I perform, I will perform now 100,000 experiments. No matter the amount of experiments that I will perform, I have 1, 1. Well, that is something else that what I have started with, right? Because I started with 0, 1. Why did this 1, yet another 1, was flipped? And it turns out that there is an explanation for it. And we distributed a negative sign into our first into our qubit 1 from the qubit 0 that we first prepared. So let's go through this. We start both as a quantum superposition, but here we start from a different Bell state than here. Notice that there is a negative sign. Now, once we tensor these, so we represent a combination of these two states, right? There is one, there is another. And when we flip the second bit, now the magic starts happen because we kind of flip from here to here, right? This is what happens. So these two change places. And now if I rewrite, this is after this our C naught operator. If I rewrite this flipped state, so notice that was C naught. C naught resulted in this flip. There is now negative into zero, into zero. I could actually represent it back yet again, but only after I multiply this by -1. So now this -1 goes out into the front of the actual state. And and now, yet again, what happens is that when I tensor this, when I go back to the previous representation of all the tensor product, look what happened. I have here, I had previously plus sign. So this is what we call a phase kickback. I applied a control X to the completely different qubit, and I got a retaliation damage into my first qubit that I didn't anticipate, right? After I go back and apply Hadamard again to go out of the quantum superposition, I see that the phase already has been applied. And this is why I got after I apply H on the minus, I get a 1 back, right? And now I have two minuses. So I have a state minus minus. In other words, what was my my state? I went from 0, 1. Then I applied an H tensor 2 to my system. I had plus minus. I applied a C naught. I had minus minus then. And now, after applying H tensor 2 again, I have 1, 1. This is something that we do not really expect at first, but it does make sense. And for example, Grover's algorithm uses this very heavily, this phase kickback. This is why it is so important to understand it. Okay, so there is a 7 p.m., 22 minutes. I think we could make a slight break. And after that, like 10 minutes to grab something to drink. And then we can go through another very nice concept, which is super dense coding, multiple gate constructions, and quantum teleportation. Actually in this order, in this exact order. So we'll go with super dense coding, multiple construct constructions, and quantum teleportation. So I think that it would be nice if we went through and made a quick, or rather some longer break, all up until 7 p.m. 35 minutes. It is in GMT plus 2 hours. So in exactly 12 minutes, how do you How do you find it? Do you feel it could be good, or do we need more time, less time? I think it's good. Okay, more? Okay, so let's prolong this to 40. Then I will give you 5 more minutes because I would like to go through the rest of the notebooks, and tomorrow we will have all the day towards we will spend entire day on Grover's algorithm and its implications, and I will showcase some more stuff if you want, if you would like to. I would also like to have a last 5 minutes on this course to establish some of the, let's say, organizational matters, and maybe do some other question and answer session, maybe queue it up in the week, but this would be towards the end of today's lecture. So let's not bother with it right now. Let's meet then in 15 minutes, exactly 15 minutes from now. So I will give you 5 more minutes. Yeah. So let's meet at 40. Okay, so everyone is here. Is everyone here? Or is there anyone that would like to have slightly longer break? Ready. Okay, so back to the topic. Uh, okay, so super dense coding. I have been programming slightly in the break, during the break, and I have decided to show you a way, another way to encode a multiple control construction, yet another way. But first, let's go over the super dense coding, and then we will have a discussion about it, about multiple control. So what is super dense coding? About entanglement, we have already said some things, right? So for example, we have a state that we already know. This is a cat plus, right? There is it is a state that represents pretty much this qubit, right? And that there are more states, but let's stay with this one for now. How do we actually obtain it? Well, there is very easy way. There is a way of applying H on the gate, right? And then what we can do is to apply to come into a Bell state, one of the entangled states, because this is like a superposition. So to come into a, let's say, cat plus plus, we would like to go through from the 0, 0, let's say, in a very simple way, and which is, oh, this is not a plus plus, actually. A plus plus would mean that there is a superposition of, let's say, 0, 1, 0, 0, 0, 1, 1, 0, and 1, 1. So I was mistaken. Yes. So and you cannot represent this situation, this Bell state as a tensor product of any sort. So, and this is why you have entangled state, as we said in day 3. So how do we do this? How do we come from, let's say, 0, 0 to a phi plus? This is like a state of one of the Bell states that describe this exact situation, where we have a plus and both of the qubits, when one is measured, the other has the same value. We could actually check this in terms of what are these? The internet, Google, Bell states, and then we have a very nice short depiction of every single state. So we would like to get this one. Oh, we'd like to get this one. How do we obtain this? Well, it is quite easily done. We usually want, when we have two qubits, we usually want to apply an H on one of them, and then to entangle them, we would like, when this is a 1, right? We will apply a conditional, let's say, instruction that this also will be 1. Whenever this is 1, this will be flipped. And since it starts from 0, it will flip onto 1 after this state, right? So after these two operations, here we have a state 0, 0, which is kind of like a C0, let's say. Here we have a C1, which is if this is Q0 and this is Q1, we have a state 0 plus. And if this is C2, we land on a Bell state, which is capital Greek phi plus. Right? This is the short way to go around this. And what can we do in this state? Where there are some nice features about this state. And one of this is that, well, we said something about utilizing the entirety of the space that we have on our unit circle, right? So for example, here we are somewhere here. I cannot draw exactly this on the unit circle because we now have an entanglement and we don't have a single qubit anymore. But this is pretty much it, right? We are in a positive, we are in a plus state. And now what we would like is, can we do something about it? Like, for example, can I utilize this space, maybe this space? I only have been, we only have been moving through this side of the unit circle so far. Maybe last time, today we went into this, let's say plus minus. So we are above, but we have explored what it is to and how it is to read from this state, right? But other than that, we didn't do much in terms of utilization of the entire space. And super dense coding aims to fix that, aims to practically gives us a way and so-called protocol on how we can encode more information in a less amount of space. What do I mean by that? Well, what we can do now is that after applying this, after preparing this state, there are several options what we could do. So we start from the superposition, right? And now one of my qubits can serve as a message carrier. Usually I could, for example, send it to someone. Let's say send my particle to Asia somewhere else. And what I could describe as a protocol to perform certain operations, whether she wants to encode some information to me, and after encoding it in terms of applying a quantum operators, she could send me back this information, this particle yet again, and I could decode this information. But look what will happen. We will use a single qubit to encode more than 1-bit information. This is how we can do this. If we would like to encode two classical bits we would apply a phase change and uh, the bit change. So we would apply to operations. So we would apply to operations either conditional z, which we didn't talk about yet, and conditional x. These conditional x and conditional z are actually not really here. These conditions, these are actually like a single gates that, let's say, once upon my qubit, my particle lands in her, in Asia's quantum machine, she could fire some certain beam that will be responsible to perform this z this z or this x. However, in this notebook, this is the notation. So we have this conditional bits, and we have certain quantum operators based on that. So we have 2 bits of information. We could encode a single qubit, and then after I receive it back, I could unpack it back into my original quantum bits. One of them will be the one that I have sent and just got back. The other one will be my original one. So this is my original one. This is the one that I send to someone. Here she encodes, gives me this back, and I unpack this. So notice that I cannot really unpack this information easily through a single experiment, because we are talking about single experiment. That's also very nice. So I could and she could encode that entangled qubit that I give her, um, and get and I can, after her operation, I could get my change qubit back, which then would mean that I could get back this information based on 2 measurements from my original qubit and my qubit that I have just received back. So this is very nice, and this is the protocol to do this. I have, for each pair, we will test it. For each pair of possible combination of bits that my recipient wants to send me back, for each combination of bits, I will have an experiment. And this experiment will be prepared like this. I have my bit that I would like to keep for myself, because this will be entangled bit that I will use later on to decode. And then I have a exchange bit that I send someone, right? Uh, I have a message recovery register. This is classical register. It will store the results of measurements back when I get my qubits back. What do? I perform a Bell state. Uh, so here um, a Bell state phi plus p plus. So this is like this 0 0 1 1. I will encode it as this. I won't throw every square root and so on. You know, you get the idea. Here the barrier is just purely for let's say graphical purposes. It doesn't need to be here. Here I encode the information. So what do I do? If I have a 0, if I have a 1 in my first qubit, uh, sorry, if sender has a 1 in his first bit, then it applies, then the sender applies an X. If the sender has the 0th bit as 1, sender applies a Z. And then what happens is that I recover my bits and I measure. So what are the results? Actually, I could decode every single combination of what sender sends me. I can decode. I can manage to decode his message or her message. If the sender send me 00, which means that pretty much there is nothing applied, I could actually show you the circuits. So this would be, I think, very beneficial to you if you will see what actually happens. So here in this case, this is the last case. This is for the last case, right? Because we apply X and Z. And remember, I started with 00. So this is, let's say, 0 and 0. I prepare the bell state. Then I have sent the one of the bits. Someone else's encodes this message with that protocol. So either X or Z to transform my bit. And now what I do is I recover this combination of bits, um, this let's say this state, and this actually makes sense if you think about it. Why do I have a 1 1 after X and Z? Recall that what we have when we do a single qubit, when we have a single qubit, I think I have a program for this. So let me have a look. What was the rotations? I think rotations. Oh, not this. So look at that. I have an X gate as my diagonal, but I also have a Z gate as my pretty much X axis. This is a Z gate. So if I prepare, let's say, a state that has a plus, my Z gate will reflect it over to minus. And then after I apply an X gate, I could land here. So I could have most of the combinations by just going either here or here, for example, minus minus, right? Or here, minus plus. I could decode any of these 4 states by applying two gates mostly. Here, I actually wouldn't have this directly, but in terms of X gate, I would need to invent something else. But it could give you the idea that it isn't as improbable as it might be. So here I could have just go to plus, then reflect from Z gate into negative minus. And after, and these two QPs that I have can be used to decode um, most of the information, all of the information, in fact. Since yes, since here, okay, so right, I could actually oh, what we could do is remove this measurement and then do a simulator here that isn't really the simulator from the air simulator, but it is a our wait, where is this? I searched something for easy copy paste, but I don't see anything. It doesn't. Okay, so let me import a simulator, state vector simulator. This is what I want. So sim equals state vector simulator. Let's probe what we have before the recovery. Because the recovery will make it so that there is only one outcome, right? And after C and X, X and Z, we will see what the state vector says. So we could run, and then we have a steer cut, shots. We don't even need shots for this, to be honest. SV equals, this is a sim job actually, because we already run the instantiation. Just after instantiation, simulation job dot result dot get state vector. And we could print this state vector. So we have a superposition of different kinds. We remember that we have a complex entries, but we never go into a complex phase, so we could just skip over this. But every single time we get another different mixture of different states. So for example, when we had a 0, 0, 0 outcome, right? This will become a 0, 0 outcome. This will become a 0, 1. This will become a 1, 0. And this will become 1, 1. So if we have a negative entry, we can see that we have a first bit set. If we have the state that is representing by the middle components, we will have a middle entry. And this is pretty much a Bell state. We get a Bell state yet again, however, in different configurations. So we could recoup this Bell state back to our desired state by just reversing the operations that we performed previously. So what our let's say what our recipient does is that we come from from this bell state, we come into yet another bell state, right? We could get E minus, let's say. We could get, let's say, C plus, capital C plus. And then after going back from it and decoding it yet again by our C naught and H, we get back our bits either unchanged, which would be 0, 0, right? Or we could get something completely different, like 1, 1, that we get as our last outcome, which is this one. So this is pretty nice because we could transform from one bell state to yet another bell state by applying different operations, and this is just on a 1 qubit, right? So we could uh, perform this operation, and then we get the outcome. We decode it using back two of our um, two of our qubits. So we get a nice compression. Okay, so I will actually turn this back into a working demo and show you this yet again. Oh, I didn't actually decode anything. Right, that was okay. So that is the circuit we can apply to actually decode uh, 2 bits of information, two classical bits, bit encoding. Uh, in a single qubit, right? Okay, so that's super dense coding. That's how it works. Um, Whether it actually happened or not in real life, I am not certain. This, when I first heard of it, this was a possibility, and it is still possibility. There were some recent attempts to send an information between distant qubits within, I think, I don't exactly know where. I think it was by light and entanglement, by light, by photons. But I have to find a document for it. I am not exactly sure where it was. Okay, so then Q80, multiple control constructions. As I said, we'll skip over to this, to Q80 first, and then we will go to quantum teleportation. So now, what are the multiple control operations? We have been talking about them slightly before, right? Because we have been talking about it during the classical systems. There was a matrix which was exactly like this, right? So here I have black characters, unfortunately. I think I could swap them now to bit. Okay, this works. So here we don't actually change anything in these halves, exactly like in a classical case. where we had these classical bits, right? Oh, no, 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 no. Where we had classical bits, is like 0, 0. We applied this C naught cont. I made a mistake, C naught conditional not, and then it was, for example, on the first bit, and we had transition to this state. There was, I think I think there was mention about it, but here it is fairly expanded because in a quantum we can do pretty much the same. You have seen this just previously, like 2 minutes ago, when we prepared a Bell state, right? Because we had this controlled X gate, which allowed us to prepare after a Hadamard, which allowed us to prepare a Bell state. So this was Q0, Q1. And this dot is what we call a control bit. And this is a bit that will be swapped. This is a target. There are more constructions like this. For example, what we could do is, let me move this slightly. Oh, I think I cannot really move that. So let me redraw this slightly towards right side. So we can, for example, do this. So what you will see in the other notebooks is this notation. So now we could do, for example, this. Now this is Q0, Q1, Q2. This is our quantum register. And now I have something else further down the line. So now the only situation that this gate would apply, because now I have two controls, right? These dots mean control. So I control on the bit 0 and on the bit 1. And what I can do with this is then I could accumulate some of the conditions from other bits. This allows us, this construction allows us to have way more depth to our circuits, because only a single control bit is, well, it is okay to, for example, super dense coding and so on, but we would like to have even more capabilities. And when we have only a single bit as a control, it doesn't really do much in terms of, for example, allowing us to have multiple controls. This allows, because we could assemble way more. Practically having this arrangement allows us to perform multiple control bits and using other, let's say, using more quantum resources, it allows us to do it. And we will explore it at the end of this notebook. So, for example, I could do something else that is also really nice. And you probably can imagine that how can I, for example, control a first bit by second and zeroth. There are constructs for this, and it only matters. What only matters is the construction of these matrices, which we'll explore just now. So for example, here we can see its effect, the C naught of this on this circuit. We can see it, and we can probe this matrix and other ones as well by constructing a circuit like this. So for example, here I have my control X. So here the situation would be like this. I have Q0, I have Q1, and I want to apply my control uh, onto a 0 qubit. Then I first, let me actually hear this. I first pass in a control bit, and then I pass in the target. There are more gates like this. For example, we have a out of the box defined yet another gate which is more complicated, which I have already told you about, which is a control node. So I have drawn you 3 qubits and then 2 dots, for example, and a box that represents that we will alter the state of the third qubit, which is Q2, because we have 0 indexing. So here we have a control qubit 1, control qubit 2, and target qubit. This is a CCX. This is already defined on the circuit, so you don't need to do anything special. You really would like to just do something like this. So let's say you have, let me actually execute this. So you can see the actual matrix. Here it is. We see that in the simple case of the C naught, we have the first entry as X. Here we have identity matrix, and here we have 0. So this is kind of like a simplified notation of this matrix that is written here. So what about this one? Well, let's make it. So for example, here we would like to use this instruction. Okay, so 0, 0, verify your implementation using unitary simulator backend. Yes, we will do. We need to perform every single one of these operations. We will perform one of them. So for example, here we have Q circuit. Quantum circuit. We will use shorter notation for this. So three qubits. 2 of them will be control qubits. 1 of them will be the target, right? And here we use this anonymous notation. So we could append 2 instructions. So first of all, we could append an X, and this will be our one. And then we could do, I think we could already use the CCX like this. So we will use 0, 1 and second as a target. Now we will simulation job. We will define it like this. Unitary simulator is already defined. That's great. So unitary simulator dot run. We don't need any shots because we are not measuring anything. And what we will do is exactly this. So dot result dot get unitary, and we will print matrix. Actually, we would like to copy every single. Oh, okay, here. C naught now 0, 1 equals, and now we would like to. Oh, there's a. Oh, circuit, right. I always forget about this. Wait, what? Oh my God, I have actually went into. Okay, I went into a solution. Okay, draw QC. So we need to draw this. That's one thing. And we need to print this. Okay, so what do we have here? We have an error, but that's fine. So the error comes from old version of NumPy because we need to do actually this, and here I will do this, and I will need to import NumPy as NP. Okay, now there is no error. So here we have slightly different situation because false. Let's do it false. So what do we have here? We have made a single gate, and this gate is a control X with the controls on Q0 and Q1. The Q2 is our target, but there's not enough to actually the simple thing, which is just single gate, is not enough because as you can see, our notation actually does not fit what we have here in these matrices. We got something different, and you can see it by examining just this matrix. So what we have is a 1 1 1, then one just here on the bottom, then again 1 1 1, and here is yet another. So this is the entire matrix. All the other entries are 0, so I will just write 0 0 0 here. But this doesn't look like the shape that we had here, right? So a simple operation like this is not really doesn't really affect the circuit in the way that this task is saying it should be. So the thing is that we would like to append the X at the end, and The reason for it is that um, we would like to fix this matrix. So we should append these x's at the same in the same order as we do in our previous case. Oh, I think I have actually botched that. Okay, never mind. I will actually come back to you with this one fixed. Anyway, we could also have even more than one or two controls. And here's an example of how you could do that. I have actually mentioned that we have a double control operations that use some auxiliary qubits. So for example, this CCX, right, allows us to practically define any type of operator that we would like to do, even like C, C, CX, and so on. We could pretty much draw in the amount of C's anywhere that we like, any amount of that we like. However, we would like to, we have to, not we would like to, we have to use an auxiliary qubit for this. And there is a reason for it. The reason for it is this. So consider that we would like to have a 3 qubits as controls, Q0, Q1, Q2. And now what we would like to have is some target. So this would be our T. And we don't have a general way to do this. Straight up out of the box gate like this does not exist. So we have to improvise. And the way that we improvise is by using as yet another qubit, which is called ancilla. This is a qubit that is extra resource, and it actually is used in many. This concept of using ancillas is used in many papers, in many algorithms. It is either used as a single ancilla or multiple ancillas. But the reason that we would like to use that is this. So we could have done this. This is our target, right? So the operation goes like follows. We and lengthen the amount of operations by first making a two-controlled gate that tie our Q1 and Q2 and affect our ancilla. And here I temporarily store the effect of Q1 and Q2, right? So here is, at this moment, if these two bits were 1, let's think about it for a second classically. So if these two operands resulted in a 1, then this bit will flip because this will always be initialized as a 0, right? So I temporarily store a 1 here. Now, what I could do is I could tie this and this into my actual target. So here's how I use more than one bit as my more than 2 bits as my control. Um, I have to use a temporary ancilla to store the temporary value and then use that temporary value whenever it is true, and this also being true, actually flips my target. So that is how you can use that to your advantage in terms of making more than 2 targets at once. Yes, Ancilla is like a helper qubit. You usually have to have um, extra resources available at the quantum hardware, right? That is why it is so hard to also perform these type of calculations, because you have to then um, try to imagine yourself something like this. Okay, I have 10 qubits that are my, let's say, my solution space. But I now need even more qubits because I need some operation, like say, let's say, quantum phase estimation. I need yet another 2 or 3 qubits to, for example, apply different operations based on the control in them and apply entire transform uh, on my original solution space, so on my original 10 qubits, and then suddenly I don't need only like a machine with 10 qubits, but I suddenly need with 15 qubits. And when I need to apply an error correction, I need to also apply even more. So this is why this is so hard to like scale these algorithms, because suddenly you need um, way more resources than you anticipated you would. And in terms of, for example, what are the conditions? What is the let's say CCCC node, right? So you probably could imagine that, okay, this could mean that I now need one ancilla, but this could mean also this another two control that I need ancilla too. So first of all, when I have 4 control qubits and then a target, I need 2 ancilla. So now I have to have a 7 qubits total to make a single calculation, right? Because I store here these two, I store on this qubit, right? I will make a kind of like a masked square. In these 2 qubits that are down here, I need to store them onto this qubit, right? On this ancilla. And then these 2 qubits, when only they are one, both, only then I will apply my final calculation, right? So this is the solution to multiple C C C C C C C C not, right? If I wanted another CC, I could have had I needed yet another A3, right, to store yet another 2 decisions, and I need yet another qubit because now look what happens. I need to end these two, so I need to do this, right? And then I can only combine 7 or 6 conditions after I have 4 ancilla. So this is a mess. There are slightly better solutions for this than trying to do this. And I have just spent like a a break that you had, showcasing and collecting my code snippets from other projects that I have prepared. And this is pretty much the result. So what you can do is to prepare a circuit with a single instruction that is defined like that. So first of all, you import an X gate from the standard library, and then you define a quantum register of 4, like control. It is control register, and once you had done this, this is your ancilla that you want to perform, or this is your target. This is the target rather. Targets. Uh, and after that, you prepare a quantum circuit. You denote that this X gate should be a control of 4 and append this multi-controlled X gate or any other gate, because there could be other gates. For example, there could be a Y gate, right? And so on and so forth, the Z gate, the multi-controller Z gate, and so on. There could be more gates for you that could be controlled like this. But usually the first thing is that that gate will need qubits, and it will need for 5 qubits. Uh, this is something that in bronze doesn't really isn't really mentioned, but this is far easier way to make any control gates, because look, you can do something like control number, and this could be like 1, 1, 2, 3, 8, whatever number, and this control number can be pretty much passed into here. So I need four qubits, for control qubits. Okay, that's fine. Here it is. Here is how you could make a parameterized gate. And then this is a problem because, okay, this is a circuit, right? This is a circuit with single gate. So how do you mm, and incorporate it into your solution? So there is another method which is compose, and you compose your this circuit, which whatever it would be, with your um, specialized one, with your smaller one. So for example, see here yet again, and there is also a operation that which is in place equals true, and it doesn't return anything. It just composes into the main solution that you want to make. And this is our results. So this is way cleaner to prepare. Does it need actually this much qubits under the hood, as I said, as I showcased you? So for example, with this CC, it requires you 1, this yet another C equals 2, yet another C equals. From this one now, we need a third, and this one is fourth, right? Does it do it under the hood? I have no idea if it does it under the hood or not, but this is way easier to prepare in terms of making making these gates by hand. It would be real painful experience to do it. Yeah, so that's pretty much pretty much sums up the task 3 as well, because we could perform these calculations, but there is yet another thing, which is quantum teleportation, which I want to talk about. And we are pretty much closing into uh, to the to the end of the lecture. So about this one, You could also see the solution here. So here it is, the 0, 0, 0 gate, and it actually works. Wait, I had the same solution. I don't know what happened. I probably selected the wrong qubits to begin with. That is why it did show something else, because I did exactly the same thing. Oh, I used the second one. Okay, so that's why. Um, I mistook this. So anyway, the teleportation. So what it is, the teleportation now. This is something that did bend my mind and even bends my mind to this day. Because this is also something that isn't really as, let's say, this isn't really something that is easy to explain. And this is about EPR paradox. If you want to know more about the EPR paradox, you are more than welcome to look up online what it actually means. But consider this. So, for example, let's say that I did exactly the same thing as with, let's say, with the super dense coding. So I have prepared a Bell state, right? Let's say this was a capital Phi plus, right? So I have a superposition. One is H, and then there is a C naught, right? Uh, and then I send one qubit somewhere completely different. Let's say I send it to um, 4 light years away, even to yet another, to Proxima Centauri. So some time passes, right? My qubit is received somewhere, and now what happens is that on their planet, they have their own qubits, and they can apply a rotation to their own qubit. Let's say this is their own qubit there. And they apply some rotation, right? Some rotation phi. And they want to transmit this state to me. So what do? They do Cx onto my qubit. So they entangle their qubit with my qubit. And what happens now is that my my state of my qubits, these are all now entangled somehow, right? So it is as if I have instantly entangled entire system, and I have it, and it is as if I can send like this information faster than the speed of light, because on their side they instantly have um, entangled their state to mine, right? And can you actually do this? Like, what is this? Okay, is this actually a proper thing to do? Well, not really, because, and I will show you this. Um, so this is pretty much the setup. I will actually draw another barrier here. After this, you see the barrier. Yes, so, oh, this is something that I did not. Yeah, so here it is. So this is my state. This is someone else's state. And what happens is that I really cannot measure this my own qubit and to just reflect uh, their own their own change that I did that they did on my qubit faster than the speed of light. Well, if you think about it, it also makes sense because, for example, what they do is that they measure their own qubits, right? But when I measure mine on my side, I only see 0 plus 1. So here I have 1 square root of 2, 1 square root of 2, as if I have just applied h. So only this side set stays. So I measure, and this is what I get. Um, and what I need is their information to actually say that, oh, this 0 that I just did with the measurement out of 101 million something qubits or shots. Oh, this 0 come from one of their own measurements. Oh, this yet another one. Now it comes from yet another their measurement. It doesn't come from my age original encoding. It does come from their actual distribution that they wanted to encode. So even though we have this paradox, it actually the only way to decode properly the information that we share together with our 3 qubits is the only possibility is when they send their measurements through classical way. And then I have to decode this state on my qubit on my end by applying these operations, and only then I can receive the correct answer. So no matter my encoding, if their measurement is I need their measurement to correct my mistakes. So for example, here I wouldn't be able to say whether the A or the B is when I make this, right? This goes phi sine phi. Whether it is this or it is something completely different, or was there any change of the phase? Was this a reflected state? Like here, for example, where there is A is near 1 and B is near 0, or is it like A 0 and minus B? So I am completely on the different in the different half of the unit circle or something else. This information is not available until I get their measurements, and their measurements can only come through a classical means of transportation. So this paradox is a paradox, but it doesn't really showcase you any way of transmitting the information faster than the speed of light that this paradox, this EPR paradox, Einstein-Podolsky-Rosen, says that there is. Um, so yeah, so this is really, really something that we shouldn't actually be so excited about, because there isn't anything to be excited about, because the paradox is solved pretty much by that outcome, that we still need that we still need to send the measurements classically to obtain the proper state on our side, even though when we entangled at the speed that is faster than light. I don't know if I have explained it really well, because this is really hard to explain. This isn't really an easy effect to explain and to reason about. This is like something like with this super dense coding. This isn't really something that is classically that happens classically. Like when I send classically one bit of information, it travels at the speed of light because the wave propagates at the speed of light, and nothing can go faster. When I encode one bit on my chip on my silicon, then this is only one bit, and here there are some different shenanigans that, for example, you could encode a quantum bit in two ways during a certain protocol, and you can extract this information back using again two quantum bits. Okay, that's fair. I have to unpack it somehow, but I could have encoded this. I could have packed this way more compact than I could encode a single bit in classical information. Here it is the same thing. I can entangle at a speed faster than light in quotation, but when I want to make a final measurement, well, I don't really get an answer until I get their answer, and their answer has to arrive at the speed of light, which isn't actually violating any paradox. Uh, Unfortunately, because we would like to send pictures faster than light, right? Especially cat pictures. Okay, so the last remark. I wanted to send you, or rather showcase you, how you could make yourself without, how can you actually run this circuit without the need of the CF information or the CF instruction if you happen to have a Qiskit 2.0 version. So that's the last thing that we will do. There is a yet another thing that I have discovered yesterday when I was testing these. So let me enter the presentation mode. And now what I will show you is this. So quantum conditional execution. So recall that we could make a quantum circuit and use it somewhere else as a part of the other circuit, right? I have showed you this today. But what you could also do is use this circuit and append it conditionally. And this is exactly what the if-else op does from the Qiskit circuit control flow module. So this operation, this instruction, this is special instruction, and it needs to be added to the circuit in some other way, uh, which I will go on to, works like this. So the if else op has several fields that needs to be uh, let's say filled in to actually make it work. First field is the classical bit that will serve as a condition. So for example, here I have a classical register bit 0, and after a measurement, this bit will turn into some value. So then what I could do is I could append this entire instruction, and first is condition. So I say that this actual register on this actual bit needs to equal 1. And you have to append, you have to in this first parameter as a tuple. Then there comes two circuits that will be executed conditionally. First one is when there is when this condition will be fulfilled. So for example, here I do this conditional gate subcircuit, right? So conditional gate subcircuit when condition is okay. Then there is another subcircuit when condition is not okay. You could leave both of them empty, or you could, for example, leave one of them unfilled. Let's say passed it as a none. So true body. This is the name of the parameter, right? It is even filled in as here. It is even filled in here, right? And this is the next one will be false body, right? So the true body will execute or will be appended once this condition is true. The false body will be appended and executed only when this condition is false. So let me get this to actually show you what it does. So first measure, and then let me draw this main circuit dot draw output MPL, so it will be easier. Let's do it as a big, and then from matplotlib import pyplot as plt to draw this circuit. So plt dot show. There is an error. Oh yeah, right. I need to remove this entire thing. Okay, so we have this zoom in. Let's zoom in even more, maybe. Oh, okay. So back to previous view. So as you can see here, this is our circuit. So now uh, we had two main registers, and we did a measurement on the bit 0. So there is a bit 0, classical. This is from our Rioveri. I messed up with the name. But now what happens is that when recovery register 0 is equal to in hexadecimal 0x1, so 1, this is a bit, right? This condition will execute, and this gate X will also be executed and will be added. What does this state do? Well, I could answer you this question. So what, because we have been doing this for some time now. So what this part of the circuit does? Can you answer me? Like, we have now reached the limit of this, but of today's lecture, but this is the last 2 minutes. So can you answer me this question, or you are too sleepy to answer this question? Oh, right. What what will this part of the circuit do? Um, okay, not really. I wanted to say what this entire assembly of two gates. So this gate and this gate, what these gates in tandem, combined will do. What will be the effect of this? This is a true, right? Because this is our control bit, right? And this H gate will occasionally flip it and will enable this condition. But what will be the effect of this? Is there? Yeah, entangled state. Bravo, right. Congratulations. Yes, you are paying attention. We have been entangling the qubits exactly like this. So this state will prepare exactly our 5 plus. 5, oh, sorry, not 0, but 5 plus. Our Bell state. But here we measure the first bit, and then we measure this into the 0. And we say that when this bit is 1, right, this condition triggers. So this condition is something else. This triggers on the classical received information, on the classical register, right? So when we have here 1, this X gate executes. And now what happens? Is any wild guess? Is there any wild guess? What will be result of that operation? Oh, I have closed it. So let me let me enlarge this for you. Oh, I might be tricky enough to enlarge it. Ah, it doesn't want. It doesn't make it bigger. Okay. So what will be here? What will be the result of this measurement on the first on the this is on the first bit, so okay, I will tell you this: bit 0 and bit 1. What will be this bit 1, and what will be this bit 1? This bit 0 and this bit 1, what they will be? Well, okay, I won't hold you more. So the result is that whenever this bit, since we have a 5 plus state, we have either 0, 0 or 1, 1, right? So if there is 1, the second bit is also always 1. In other words, when we read 0 when we read 1 into our bit 0, this triggers, and this always flip this 1 into 0 again. So we never get this state. This state will never appear. We will either have 0, 0 or 0, 1, right? And we can check this if this is a true. So now I will turn off this showcase, and I will perform 1000 experiments, right? And this is exactly what we do. See. So we would have seen 1, 1 here, right? If I disable this if else op, this is what we see. We see 1, 1 and 0, 0. Exactly. But when I enable this conditional if-else, I still have this one qubit that is left to be evaluated. So I can still perform some calculations before I take measure, and I just flip it back to 0, right? And as a result, I never get on my second quantum bit. On first quantum bit, I get a superposition, but on a second quantum bit, I never get anything else than 0. Okay, and so by using these if-else ops, I could prepare this experiment and let's say alleviate this um, let's say um, this operation that is missing from alleviate this problem of having this operation removed from Qiskit 2.0, because the CIF is exactly the if else op. It would be here, right? And I could control this by just preparing a single circuit with one gate, and that's all. That's it. So that would be the method to actually recover from this notebook if you had a Qiskit 2.0 installed. Okay, so that was it for today's lecture. I'm sorry that I kept you longer than I thought, 7 minutes longer, but I think I had told you about pretty much everything that you need to know, and also even more, because I have showcased you some differences between the Qiskit 2.1 to 2.0, 2.1, 2.2, and Qiskit 1.0 with this if-else op. Actually, there was one more difference. For example, in the Qiskit 1.0, there was a QASM simulator. This is no longer existing in Qiskit 2.2, so we have modified this. I have showed you the seed simulator setting, which makes it a viable alternative to test repeatably on partially randomized thing, because we could just set it together on the same number and it would perform exactly the same thing on my end and on your end. Right. So I have showed you some possible ways to test your quantum applications as well with the usage of some alternative methods. And I have, as the last thing, I have showed you the multiple control constructions. I have showed you this. So this extended way of preparing controlled gates that are arbitrary. This is something that isn't here in QBronze, so thank you very much for joining me today. And see you tomorrow for the last lecture on this topic, which will be the actual Grover algorithm. So thank you very much. If you have another questions, then I could stay slightly longer. I do not mind really. I think I could also prepare some sessions, so some Q&A session, because I've seen in QBronze Discord that there have been some people that wanted a partner or something like that to make some sort of another session, another learning session, or to I could spend like an hour to clear up some questions if they arise. Just send me a message in and we could schedule one before your deadlines for quizzes. Yes, before the deadlines on quizzes. Because the first one is 16th October, if I am not mistaken. So thank you very much and see you.